Hello there, General Aviation Fixed Wing pilots in training. Today, the mysterious weather magicians are here to present to you an informative presentation on the importance of density altitude. The concept of density altitude should be brought to your attention early on in your training and instilled within your mind, since our constant companion air can undergo changes that affect the performance characteristics of flight. Before we define density altitude, let's test your pre-knowledge and play to fly or not to fly. Are you ready? Then go ahead and buckle on in and imagine for a moment. You're planning to take off from Sky Harbor in Phoenix, Arizona. The airport elevation is 1,135 feet above mean sea level. Scenario 1. The airport station pressure in inches of mercury is 28.71. The temperature is 120 degrees Fahrenheit, and the dew point temperature is 30 degrees Fahrenheit. Scenario 2. The airport station pressure in inches of mercury is 28.71. The temperature is 60 degrees Fahrenheit, and the dew point temperature is 30 degrees Fahrenheit. Can you guess which scenario will produce a higher density altitude? Keep that answer in the back of your mind, and we will swing on back near the end of the presentation to answer it. Let's begin. FAA defines density altitude as the pressure altitude corrected for non-standard temperature. In other words, the altitude the airplane thinks it is at and performs in accordance with. A 1 inch by 1 inch column of air extending from sea level to the top of the atmosphere will exert a sea level pressure of 14.7 psi, or 29.92 inches of mercury, or 1013.25 millibars. As you climb in altitude, pressure decreases. Based on the graph, at 13 kilometers, 8 miles above the atmosphere, where pressure is near 180 millibars, or 5 inches of mercury, you would be above 90% of all the atmosphere's molecules. Pressure and temperature are directly related. The French physicist Jacques Charles formulated from his experiments a formula to express an observable law of nature. The volume of a given mass of an ideal gas is directly proportional to its temperature. Standard temperature is 59 degrees Fahrenheit, 15 degrees Celsius, and changes by 3.5 degrees Fahrenheit, 2 degrees Celsius per 1,000 feet. Albert Einstein once said, "Everything in life is vibration." Temperature plays an important part in the movement of air molecules. Hot air excites the air molecules, which pick up speed and begin to expand in all directions. The hot air is less dense, meaning there are fewer molecules in a given volume of air. Cold air restricts molecular movement, and molecules condense or slow down and come together to increase density. Let's visualize a hot air balloon. A burner heats the air in the envelope, and the molecules thermally expand and reach warmer temperatures than the surrounding cooler air. The warmer, less dense air is more buoyant and overcomes gravitational forces to lift upward. A naturally aspirated reciprocating engine needs the proper fuel-air mixture to produce normal engine performance. The FAA defines the stoichiometric mixture as the fuel-air mixture ratio that, when burned, leaves no uncombined oxygen nor any free carbon. It releases the maximum amount of heat and therefore produces the highest exhaust gas temperature. A stoichiometric mixture of gasoline and air contains 15 pounds of air for 1 pound of gasoline. Figure 2-12 gives a visual indication of the changes in fuel-air mixture with increased altitude without leaning. We can see then that as the aircraft climbs in altitude, the fuel-air mixture would naturally become more rich. A rich mixture contains more fuel than air, and the engine does not have sufficient air to breathe. A loss of power and waste of fuel can make a long planned trip much shorter than intended. A crowd is forming around two distinct canvases. On the canvas to the left, the artist depicts an aircraft in a nose-down dive, struggling to generate enough lift across the surface of the wings to keep the aircraft airborne. On the canvas to the right, the artist depicts an aircraft in a nose-up configuration and comfortably climbing in altitude with an abundance of air molecules packed closely together. Let's take a look at two common phrases that show how temperature affects the height of constant pressure surfaces. High to low, look out below. When the plane enters an area of colder, lower pressure, the aneroid wafers expand and the indicating pointers move clockwise. Watch how the plane changes in height. Without corrections, the indicated altitude on the face of the instrument is higher than the aircraft's true altitude, which is lower. Low to high, clear the sky. When the plane enters an area of warmer, higher pressure, the aneroid wafers compress, and the indicating pointers move counterclockwise. Watch how the plane changes in height. Without corrections, the indicated altitude on the face of the instrument is lower than the aircraft's true altitude, which is higher. How do I calculate density altitude? Good question. Let's begin by reviewing the formula for pressure altitude. The formula for pressure altitude is the true altitude plus 29.902 minus the atmospheric pressure times 1000. Breaking down the formula, we can see that the true altitude is the aircraft's actual height above sea level. The local atmospheric pressure is subtracted from the standard pressure to get the conversion factor, which is multiplied by the constant 1000, because in a standard atmosphere, air pressure decreases by 1 inch of mercury per 1000 feet. Plugging in the numbers for scenario 1 from the first slide, and we get 1,135 plus 29.902 minus 28.71 times 1,000 equals a pressure altitude of 2,345. The formula for density altitude is the pressure altitude plus 120 times the outside air temperature minus ISA temperature in degrees Celsius. Breaking down the formula, 120 is a constant. The International Standard Atmosphere, ISA, is the model of the atmosphere when sea level pressure is 29.902 inches of mercury and temperature is 15 degrees Celsius. To determine the ISA temperature for the formula, we need to know the temperature of the air at 2,345 feet by using a model chart. Finishing up with scenario 1, and we get 2,345 plus 120 times 49 degrees Celsius minus 11 degrees Celsius equals a density altitude of 6,905. Let's take a look at how a E6B flight calculator can be used instead to find the density altitude for scenario 2. Density altitude will be shown in the middle window of the E6B flight computer when the air temperature is set over the pressure altitude. The air temperature in scenario 2 is 60 degrees Fahrenheit, which is 15 degrees Celsius. Our pressure altitude has remained the same at 2,345 feet. We will go ahead and rotate the inner ring clockwise to attain our density altitude. The density altitude can now be read in the center window, and it indicates approximately 2,500 feet. To answer our original question, scenario 1, which has a density altitude of 6,905 feet, is much greater than scenario 2. Let's see how a high density altitude takeoff can affect performance. It is generally better to fly early in the morning or later in the evening when temperatures are lower to avoid a possible high density altitude takeoff. Ensure you review your local airport diagram to ascertain the lengths of the runways so you have an idea if you'll be able to accomplish a longer takeoff roll to get up to speed. The Pilot Operating Handbook, POH, will contain useful information like charts that give you speed recommendations based on atmospheric conditions. It's best to observe these recommendations to avoid a mishap. Flaps are not lowered in a high density altitude situation since the increase in drag will lower the speed of the takeoff roll. Also, weight considerations will need to be made, and it may be wiser to unload some luggage and make one or more trips. Too much fuel? Calculate only what you need, including 30 minutes of reserves. To conclude with the presentation, the mysterious weather magicians would like to thank you for your time today and that we are always here, weather spying to prevent you from dying.